This video is for Chemistry in the Earth System, Unit 1.2, Thermochemistry. Today's essential question is, what is the relationship between chemical changes and changes in energy? What is the relationship between chemical changes and changes in energy? Our first main idea, activation energy. Activation energy. Burning a strip of magnesium metal is an exothermic reaction. As the reactants change into products, there is a decrease in enthalpy as energy is released. The change in enthalpy in this reaction is the heat of the reaction. The energy of the product, magnesium oxide, which is what you get when you burn magnesium metal, is lower than the combined energy of the reactants. So the energy of the product is lower than the combined energy of the reactants. We can see that on the screen here. Although the reaction is exothermic overall, some energy, however, must be supplied to the magnesium to begin the reaction. Right? So overall, there's a reduction in energy, but to start the reaction, we must activate. So activation energy is the energy needed to begin a reaction. In the case of this magnesium, an open flame will supply that energy, and you can burn magnesium simply by putting it into a flame. But what about the reverse action? In the reverse direction, the activation energy is much higher than in the forward direction. This is because the products are at a lower energy than the reactants. So, in the reverse direction, the reaction's change in enthalpy has the same value but the opposite sign as that of the forward reaction. If the forward reaction is exothermic, the reverse reaction is endothermic, but the amount of the enthalpy change is the same. Only the sign is reversed. And we can see, if I go back, and we can see that the delta H here is the same value. However, notice that the arrow is pointing in different directions. We have energy leaving the system and energy going into the system. Therefore, the signs must change to reflect that direction. Our next main idea, Hess's law. Hess's law. In calorimetry, we could do experiments to calculate the heat associated with the chemical and physical changes. But not all reactions happen that quickly. There are two methods that are used to calculate heat changes with chemical reactions. One is Hess's law, which will be examined here. So, imagine two different hikers climbing to the top of a mountain. One of the hikers go straight up the mountain. The other reaches the top, the same point, by a path that meanders up and down the sides of the mountain. The main takeaway is, at the end, the net change in position for each hiker is the same. So, chemical reactions present a similar situation. Hess's law states that the enthalpy change of a reaction is the same no matter how many intermediate steps occur. Like the hikers, the reaction will have the same net enthalpy change whether it occurs as a single reaction or as the result of several reactions. When combining equations, which is what we will do using Hess's law, keep in mind the following points. If you reverse an equation, change the sign of the enthalpy change from negative to positive or vice versa, from positive to negative. Also, if you multiply the coefficients in an equation, you must multiply the enthalpy change by the same factor. So keep those two things in mind. So let's look at an example. Determine the enthalpy for the reaction of sulfur with oxygen to form sulfur trioxide, according to the following equation. So we'll be solving for delta H. Now, we have access, and you will always have access to a set of equations that represent reactions with known enthalpies. And you'll be using Hess's law to combine and manipulate these values to figure out the overall enthalpy. So these are the two reactions that we have access to. We know that solid sulfur reacts with gaseous oxygen to form gaseous sulfur dioxide with an enthalpy change of minus 297 kilojoules. We also have access to the equation: two sulfur trioxides in the gaseous state decompose into two gaseous sulfur dioxides and one gaseous oxygen molecule with a delta H of 198 kilojoules. So we're going to use this information and then manipulate these equations to find our answer. So what we will do is, again, we need to continue to reference the reactions that are known and can be used. First, we will multiply the first reaction by 2. So because we're going to multiply everything in that equation, in that reaction equation by 2, we're going to distribute that to all of the coefficients. Now, in the example we're using here, the coefficient starts out as 1 for all 3 species. Once we're multiplying everything by 2, it now becomes a 2 coefficient for all of the terms. Now remember, because we are manipulating this equation by multiplying it by 2, we also have to multiply the enthalpy change by 2. Next up, we will reverse the second reaction so that it now reads as a synthesis reaction. 2 SO2s plus 1 O2 react to form 2 SO3s. Now, because we are reversing this reaction, meaning we're looking at the reverse direction, that means the direction of the enthalpy change is also changing. So we need to flip the original delta H, which we had as a reference, positive 198 kilojoules. We're going to flip that sign because we flipped the reaction. So now the delta H that we have access to is minus 198 kilojoules. Finally, we're going to combine the two reactions, making sure when adding reactions A and B that they add up to make the desired reaction, right? The reaction that we're trying to solve the enthalpy for, and we can add the enthalpies that we've been given. And so in this example, we notice that because the second equation was reversed, the enthalpy changed from positive 198 kilojoules to negative 198 kilojoules. So when we add these values, right, double the first enthalpy and then reverse the second enthalpy, they add up to negative 792 kilojoules, meaning 792 kilojoules leaving the system. Our next main idea, heat of reactions. Heat of reactions. It is practically impossible to gather data on the enthalpy change of every reaction that exists. There are simply too many reactions, and the change in enthalpy of a reaction is subject to a number of factors, including temperature. To help standardize enthalpy change values, chemists have assembled data for many reactions, some of which are shown in the table on the screen here. In these standardized reactions, the reactants and products are at specified thermodynamic conditions of 25 degrees Celsius and 1 atmosphere of pressure. Now, these conditions will differ from the standard temperature and pressure used in the study of gases when we get to there. Now, the symbol for the enthalpy change of a reaction at standard conditions is shown on the screen here, delta H naught sub Rxn. Again, this is the symbol for the enthalpy change for a reaction at standard conditions. Again, 25 degrees Celsius, 1 atmosphere of pressure. The naught symbol indicates standard conditions. That's why the naught symbol is there. To make it easier, chemists use tables of heats of reactions. The heat of reaction is the change in the enthalpy of a chemical reaction that occurs at a constant pressure in which 1 mole of a substance is formed from its elements. These values are called standard heats of formation, represented by delta H naught sub F. The standard heat of formation of an element is defined as 0 kilojoules per mole. Now, using standard heats of formation, the heat of reaction is calculated by subtracting the total heat of formation of the reactants from the total heat of formation of the products. So the formula for calculating the heat of a reaction can be written as delta H naught reaction is equal to delta H naught products subtract delta H naught of the reactants. Because the standard heats of formation are expressed in kilojoules per mole, the heat of formation for a specific compound must be multiplied by the coefficient of the substance in the balanced equation. So, the use of standard heats of formation combines the equations for the formation of products in the reaction. Each of these equations is then multiplied by the coefficient in the desired equation, and the equations for the reactants are reversed. Hence, their total enthalpy change is subtracted. The effect is the same as breaking down the reactants to elements, and then combining the elements to form the products. Let's take a look at a sample problem. Calculate the standard heat of reaction for the complete combustion of ethanol, which is C2H5OH. So, in order to combust something, we must combine it with oxygen by definition. So, we will combine our ethanol with oxygen to yield carbon dioxide and water, standard products of the combustion of a hydrocarbon, and then balance the equation, hence the coefficients. So, how do we solve it? The standard heat of reaction is calculated using Hess's law, according to the equation on the screen here. For this reaction, the equation becomes 2 moles of the heat of formation of CO2 plus 3 moles of heat of formation for the water, subtract 1 mole times the heat of formation of the ethanol, plus 3 moles times the heat of formation for oxygen gas. Now, you will be looking up these values, right, these delta H's, from a table. They are not to be memorized. So we can simply substitute in the values from those tables into the equations and then solve using a calculator. Now, if you use your order of operations correctly, in this particular example, you have a final answer of negative 1,235.4 kilojoules. At this point, you should be able to generate a full and appropriate response to today's essential question. What is the relationship between chemical changes and changes in energy?